You're all connected?
Yeah.
You can hear me also, right?
Yes.
Okay. Okay. So, yeah, what were we discussing last time? Yeah, just to remind you, if I see three Lie algebra, the first step was to look at the cartan. This is generally true. We'll for all the Lie algebras we'll be discussing later, next weeks. This is the step. These are the steps. So first find some cartans of algebra, some convenient one. So in this case, we call it H1 and H2, generated by H1 and H2. So this is two-dimensional cartans of algebra, and we chose the basis, chose the basis of H1 and H2. Right? And more precisely, H1 was just the sigma 3 in the top block, top 2 by 2 block, and everything else 0. And H2 we chose to be the bottom 2 by 2 block, and again sigma 3. This was convenient choice. And then the next step was to determine the eigenvectors. Eigenvectors under the adjoint action. Adjoint action. Okay. In order to do that, in order to find the eigenfunctions, you are forced to complexify, right? Because you see, these are Hermitian operators, but nevertheless, the adjoint or the cartan is Hermitian, right? But nevertheless, when you look at the eigenvalues, eigenvalues are real, right? But eigenfunctions in general are not real. Right? So that's why we need to. So for this, we needed to complexify. But this is not a problem. We complexify to understand the structure, and then we can go back to the original basis by taking suitable combinations of these complex ones. So this is the intermediate step. And we found that there were 6 eigenvectors, because after all, total dimension was 8, out of which 2 2 dimensions are the cartans of algebra, the remaining guys are 6-dimensional. So we could find exactly the 6 eigenvectors. And the eigenvectors we called, I think, x plus minus alpha 1, x plus minus alpha 2, and x plus minus alpha 3. So these were, what were the, I think, yeah, these were simply, you think x plus minus alpha 1 was, if you think of this particular SU2, if you focus on this 2 by 2 block, then just take this is sigma 3, and the corresponding ones will be the upper one. So x plus alpha 1, the plus 1 was 0, 1, 0, 0, 0. So I think we already used the notation E12, and this was E21, right? The plus and minus sign. This was a plus sign and minus sign. E12, E21. And this one was E23, and again with the plus sign, and the minus sign it was E32. And with here it was E13, and with the minus sign E31. So you found that. And then, so what were the eigenvalues? So the one convenient way to summarize this is just to specify the eigenvectors. Eigenvalues with respect to H1 and H2. So these are So we found that this eigenvalue was, if I write so I'll label H1 eigenvalue, more precisely add H1 eigenvalue, and add H2 eigenvalue in this order. So in this order, we'll just put, so first one, E1, the plus sign was 2 minus 1, and the minus sign was minus 2, 1. So it's just the opposite signs. So this was plus 2, this became minus 2, this was minus 1, that became plus 1. I think this is correct, right? And if you, okay, E23 was minus 1, comma 2 for the top one, for the plus sign, the plus alpha 2. So this is E plus alpha 1. In this notation, we are just denoting this by the eigenvalues. And this is E minus alpha 1. This one is E alpha 2 plus alpha 2, which is denoted by minus 1, 2, and E minus alpha 2, which is denoted by 1, minus 2. And finally, for E alpha 3, E plus alpha 3, it was a combination, and we found that this was denoted by 1, comma 1, and E minus alpha 3 is minus 1. Right? This was from the last time. The other thing, yeah, okay, so this is the basic structure. And of course, there are commutation relations. Let's look at the commutation relations between these guys. We know the commutation relation between H1 and all of this, and similarly H2 and all of that. Those are the eigenvalues. Those are the eigenvalues, right?
The roots, right? They are called
the roots, yeah.
And they are also the weight for the FH.
Exactly, exactly. So, I mean, these are the weights for the adjoint representation. Usually, there's a special name for the adjoint representation. We call it roots. For every other representation, we just call them weights. That is because this root, this is directly related to the, I mean, roots are something special. Because those are associated with the generators themselves. Whereas other representations are not. Other representations are where the generators are going to act, right? But here the generator, the space, the adjoint representation, the vectors which exist, the space which exists inside there, that itself are the generators. So they're special. So for this reason we do that. Okay. So we found that, so these are the, for example, what does it mean? This means, these numbers just mean, for example, E plus alpha 1, H1, with the commutation relation of that was simply 2 times E plus alpha 1. Right? So this number 2, this is the eigenvalue, the H1. Okay, so this is fine. So this information already tells you how the result of the commutation relations between the Cartan generators and the remaining ones. What about the commutation relations between them? Okay. So for this, so now you ask the question, the commutation relations between the remaining generators. So between, say, E alpha 1 with E alpha 2, etc., etc. Right? So all of these things, all of these remaining ones, don't pass. And for that, it's just easy to see. So the first thing that we proved in general, that if I take the commutator with the E alpha 1 and E alpha 2 and ask the question, what is this? Is it an eigenvector of the add H1 and add H2? And if so, what is the eigenvalue? Right? That we have done several times. So the conclusion from that was that if I look at the commutation, for example, of H1 or any H with the E alpha 1, E alpha 2, that by using the Jacobi is the same as H E alpha 1, the Jacobi identity with the E alpha 2, plus E alpha 1, H E alpha 2. Okay. So from this we concluded, this commutator will just give you this number, 2 times E alpha 1, and this one will give you whatever the number is for alpha 2, minus 1 times alpha 2. So both are some numbers, right? So this is going to be alpha 1 H. This was again another notation we used. Remember, we were thinking of, alphas live actually in the dual vector space. So this was the notation. So this is simply E alpha 1, E alpha 2, and this one is alpha 2H. This is a number, so I can take it out, and again E alpha 1, E alpha 2. Okay. So therefore you see that, so the whole thing becomes alpha 1h plus alpha 2h times this. So this is again an eigenvector. So the eigenvalue of this one, of this guy, the eigenvalue is simply alpha 1h plus alpha 2h. The eigenvalue. So the eigenvalues just add up, right? So the first thing, so that immediately tells you that if I look at this commutator, and suppose I find that some eigenvalue which does not exist, which is not one of these 6, then it must be 0, right? Because this is all we have. Whatever it is going to be inside the algebra. It's not going to take you out of the algebra, right? So it should be one of these, some combination of these 6 guys, right? Or even 8 guys for that matter. Yeah? Okay. But if this root does not exist, then it's automatically 0. Okay. So for example, so if I look at the commutation relation of, say, let's say E alpha 1 with E alpha 3, okay, then these numbers will add up, right? So you will get 2 plus 1, 3, 3 comma 0, right? But 3 comma 0 doesn't exist here. Right? So therefore we conclude, because of this fact, that many of the commutators are 0. So E alpha 1 with E alpha 3 is 0. Okay. E alpha 1 with E alpha 2 of course we could have checked it by explicitly looking at this commutation relation. But what I'm saying is you don't even have to do that. Just by looking at the eigenvalues, you can already say what is 0 and what is not 0. So if I look at alpha 1 with alpha 2, then you see this becomes 1, 2 minus 1, 1, and this is also 2 minus 1, 1, and that exists. Okay? So therefore, whatever it is, this should be proportional to E alpha 3. What about E alpha 1 with E minus alpha 2? Well, E alpha 1 with E minus alpha 2, so you have to add these two guys. Now you see again, this becomes 3 comma minus 3. It doesn't exist. So it is 0. And in fact, you can see that if you take plus minus or minus, and with a minus plus in that order, plus with minus, minus with plus is all 0. And here, if you take plus minus with plus minus here, then you will get here plus minus alpha 3. I mean something proportional to plus minus alpha 3. So a lot of these commutators you immediately see. Is there anything else left? Yeah, we can look at the commutation relations with alpha 3. Suppose I look at E alpha 1 with E alpha 3. Alpha 1 with alpha 3. So we add, again, this doesn't exist. 2 plus 1, 3, but 3 doesn't exist anywhere. So that is 0. But what about, okay, alpha 3 plus minus is 0. What about E minus plus alpha 1 and E plus minus alpha 3? So we want to take E minus alpha 1 with E alpha 3. Okay. So minus 2 plus 1 is minus 1, and 1 plus 1, 2, that exists, right? So this is E alpha 2, proportional to E alpha 2. That is for the top sign, and the bottom sign will be exactly the opposite sign, so it will be E minus alpha 2, plus minus alpha 2. Because you see the signs are arranged so that the eigenvalues are just flipping the signs, no? So plus alpha 1, you see both these signs flipped from plus alpha 1, same thing. So therefore that works. And then we have E alpha 2. If I look at alpha 2 with E alpha 3, say take the plus combination, for example, plus alpha 2 with plus alpha 3 again doesn't exist. 2 plus 1, 3 doesn't exist. So we can look at again the minus sign here. If I look at the minus sign, so E minus alpha 2 with E alpha 3 gives you 2 minus 1, right? 2 minus 1 is alpha 1. So this commutator is alpha 1. And again, if I flip all the signs, then this will become plus minus alpha 1. So these are all, I mean, there are still a few more commutation relations. What about alpha 1 with minus alpha 1? So if I look at the final commutation relations here, E plus alpha 1 with the E minus alpha 1. Well, if you add up the two eigenvalues, it becomes 0. So it must be in the Cartan. Okay. So this must be in the Cartan. Okay, all of them, alpha. Same thing happens for the, and you can actually check that it is some number times H1. I mean, one can work it out explicitly, but I think it is just H1 only, right? This is H1. And alpha 2 with the E minus alpha 2 is H2. And finally, E alpha 3 with E minus alpha 3 is some combination of H1 and H2, right? I think you can check that, alpha 3.
I think it was also H1 plus H2.
H1 plus H2, yeah. So, okay, so so it's this particular combination. And everything else, yeah, that is it. I think that's all we have, right? Is there any other possibility that we have missed here? So this was plus minus was vanishing. No, plus minus, well, that is 0. Did we? Yeah, I think we have taken into account everything, right?
In the literature notes, Professor, there was this equation which has n, a, b instead of these coefficients. And in the derivation, do we have like to substitute each and every commutation relation, or just like drive it from the diagram? From
which equation are you talking about? N. N was there was an N there? N alpha beta. Yeah. N alpha beta, exactly. Yeah.
Yes, 8, 4, 6.
Yeah. So the content of that exercise was the x alpha x beta commutator is equal to some number times x alpha plus beta. But that is simply the statement that the weights, the roots add up. Right? So that's a statement. And of course, this coefficient of n alpha beta a priori could have been 0, right? But it turns out one can actually prove that it can never be 0. In this particular case, we can check explicitly, right? But in more general, I mean, that will be the content of the next lectures. We prove that for all certain types of algebras that we are interested in, this is not going to be 0. Right? So if the roots are allowed, then the coefficient will not be 0. Yes. Okay. So this I think I don't want to erase this, but anyway, let's see. Now, this was for the adjoint representation. Now, what about other representations? So the structure was, again, the important point was the structure was that, so the next step, the next step was the following. We define a concept of positive roots. That is what we will call like creation and, raising and lowering operators, not creation, raising and lowering operators, like we did for the SU2, the J plus and J minus. J plus was increasing the eigenvalue, J minus was decreasing the eigenvalue, right? I think I was calling J plus, I'm not sure. Anyway, for SU2, there was a H and E plus and E minus, yeah. That was it. So E plus we called it as a raising operator and E minus lowering operator because E plus was increasing the eigenvalue of H in units of 1. In this case it was 1 because we had normalized. This was really sigma 3 by 2. Right? Here we are taking sigma 3. So it will increase in steps of 2 because of this extra factor of 2. So similarly we have to do here. But you see, this is now we are talking about Cartan generators which are in 2 dimensions. Cartan generators are spanning 2-dimensional space. And the roots are also living in 2-dimensional space, the dual vector space, right? So what is the concept of positive and negative? So you have to make some definition about that. And we said, okay, the idea was that, so if I draw all these roots, so let's say this was 2, I will not put the, you see, before we were drawing, we drew this figure where you had a nice hexagon, right? With a nice hexagon. But that was not, we are not plotting H2 and H1 eigenvalues. We were plotting the eigenvalues of H1 and which was, I think we were called, that was lambda 3, which is the same as H1. And we are using lambda 8 to plot here. No? But now, this is not very useful. I will explain to you the reason for that. Because lambda 8 was this, 1, 1, minus 2. You see, this is not coming out in any simple way as the, I mean, what was the point of this? I mean, this, in the SU2 case, the commutation relation of E plus E minus, E plus with E minus was H, some number times H. So this will not be part of an SU2 subalgebra. I mean, some like sigma 3, like, no? It's not an SU. So it is better to use H1 and H2 if you want to. In the end of the, on Friday, I was trying to construct some representations, right? So there, what we were doing, we were using the raising and lowering operators. But when it raises or lowers the eigenvalues, it raises the eigenvalues of H1 and H2. It is much more, I mean, one can of course track it also for lambda 8, but it is more inconvenient. Okay? You can work it out also with lambda 8. But more direct, it's more direct to look at the eigenvalues of H1 and H2, which are in this, there are two SU2 subalgebras, which we used, x alpha 1, x minus alpha 1, and H1. This formed one SU2 subalgebra, and x alpha 2, x minus alpha 2, and H2. It formed another SU2 subalgebra. There is more, but alpha 3, x minus alpha 3, and H1 plus H2. Not A, H1 plus H2, right? Some H1 plus H2. H1 plus H2. So this, yeah, actually it was this combination. Whatever is appearing here, no? Because this will form one SU2 subalgebra. Okay. So this way another SU2 subalgebra. So what I will do now is to just write the eigenvalues with respect to H1 and H2. So there was this point which was we were calling E alpha 1, right? But I will label it now with the eigenvalues with respect to H1 and H2. Okay? And that is nothing else but 2, minus 1. Right? Similarly, then you had this what we were saying, this one we were calling X alpha 2 or E alpha 2. I mean X, I don't know, I'm using E alpha 2. And this, again, I will label with its eigenvalues. So it was minus 1, 2. And here is E alpha 3. This was, again, labeled with that, so it's 1, 1, right? And then the negative ones are exactly the opposite roots. So this one was E minus alpha 2. So maybe I shouldn't draw like this, so just like that. This is. Okay. So these are the roots. Okay. So this is E minus alpha 1, which had the opposite of that. So it is minus 2, 1. E minus alpha 3, which has minus 1, and minus alpha 2, which is labeled as 1, minus 2. Okay, so that is the label. Now the idea was, I mean, so the question was, I mean, in this thing there is nothing, what do I mean by positive or negative? Okay? So the way to define this, I mean, in this plane, this is a plane, right? So I should divide the plane into two halves and say everything on one side I will call positive, everything on the other side I will call negative. But when you choose the plane, you have to make sure, the line, you have to make sure that the line is not passing through any of these points, right? Because if the line was passing, for example, like that, then you will not know what to say, whether this is positive or negative, no? So choose something, some line, for example, let's say this line, right? Some line, any line, arbitrary line, so that so long as it doesn't pass through the roots. And declare that one side is positive, and other side is negative. So all those objects, all those roots which are on this side, I call them as raising operators. So in this example, for this choice, alpha 1, alpha 3, alpha 2, these are all positive roots with this choice. If I had chosen, for example, this one here, positive roots will be alpha 3, alpha 1, and minus alpha 2. But it doesn't matter. It's a matter of your choice. The results will be the same. So I choose like this here. So these guys, these three are positive. E alpha 1, E alpha 2, and E alpha 3. These are positive root vectors. Positive root vectors. And the alpha 1, alpha 2, alpha 3 themselves are called positive roots. Okay. So alpha 1, alpha 2, alpha 3 are positive roots. All right. For every positive root, there is also a negative root indeed. Alpha 1 minus alpha 1, alpha 2 minus alpha 2, alpha 3 minus alpha 3. So this way of dividing into positive and negative, half of the roots are positive, half of the roots are negative. And for each of this positive root, there is an SU2 subalgebra. I mean, the E alpha 1, E minus alpha 1, and one combination of the Cartan subgenerators, which in this case is H1. Okay. Similarly, E alpha 2, E minus alpha 2, H2. I point here for H1 and H2 because those are Cartans, so they are like zero eigenvectors, zero eigenvalues, right? Because they commute with each other. So they are zero, that's why I'm pointing here. And alpha 3 minus alpha 3, and with H1 plus H2, that forms another SU2 subalgebra. Okay, so now, just like in SU2, what we did, in SU2 case, we said, I will declare this guy as the raising operator, let's say the positive one in that case, and this positive root vector, this is a negative root vector, lowering operator, and then we define the highest weight state as a state in any representation, highest weight state in any representation, as the state which is annihilated by the raising operator. And we are guaranteed such a state exists because the representation is finite dimensional. So we said, okay, I will take the highest weight state which is annihilated by E plus. And then get all the other states in the representation by applying lowering operators until you hit the lowest weight state. So after that, again, there's nothing. So the same idea is here also. So what we do, should I erase that? I mean, it is, I think it's all given in that page, right? So that if I have to refer to that, yeah, I mean 8.47, no? All this information is given. The exercise 8.5. What are these n coefficients, right? So, okay. So I think I have to erase this, otherwise there's no space. So let's see. So I will define now the highest weight state. As something which is annihilated by, so this is annihilated by highest weight state, is annihilated by E plus alpha 1 or E plus alpha 2 or E plus alpha 3. It is annihilated by all three. Right? We want to say that any one of them acting on this gives you 0. So of course now I should really be more careful. I should put here in the representation, no? Because now we are not, so in that representation. So all of these three operators acting on that simultaneously annihilate each other. So this is the definition of the highest weight state. However, this has too many conditions here. Because indeed, I mean, we know that E alpha 1, E alpha 2 commutator is E alpha 3. Some number times here, some non-zero number times E alpha 3, right? So if I have already ensured So this in particular means, because representation has to satisfy this commutation relation, it implies RE alpha 1, RE alpha 2, commutator is RE alpha 3. So if now I apply, if I have already guaranteed that these two annihilate the highest weight state, then we get it for free that this also annihilates it, right? Because this guy is nothing else but the commutator acting on the highest weight. But commutator will be, there will be two terms here, RE alpha 1, RE alpha 2, minus the other way around. For the first term, we already know that RE alpha 2 annihilates it. Second term, we already know that RE alpha 1 annihilates it. So it is for free. You get for free that if you satisfy this condition, these two conditions, then this condition is automatically satisfied. Is automatically satisfied. Okay. Yeah, and yeah, this is an important point. So you only need to check these two things. Okay. You don't need to do anything else. And then we label the highest weight state by specifying, okay, there will be RH1 and RH2 acting on this highest weight state, acting on highest weight state and highest weight state. It will be, it will have some eigenvalue, and let's call this W1, HWS, and W2, HWS. Sorry, these are some numbers. But these numbers cannot be arbitrary. You see, we know, because these three things form an SU2 subalgebra, these three things form an SU2 subalgebra, then I know the eigenvalues of these guys must be integer. Right? Cannot be, again, in SU2 we remember it's integer or half integer. But our H1 and H2 were 2 times sigma 3. Right? Our H1 is sigma 3, whereas there it was sigma 3 by 2. So it is 2 times the normalization we use for SU2. Right? So if with a sigma 3 by 2, eigenvalues were half or integer, half integer or integer, eigenvalues of H1 and H2 will be integers. Right? So we know these guys are going to be integers. Both W1 and W2 will be integers. And what is more, it will be positive integers, because these are the positive, these are the raising operators, right? So it will be positive integers. So this will be positive integers. Okay. So more generally, in the notation that we use in the sense of dual vectors, if you write R of H, where H is an arbitrary vector of the Cartan subalgebra, then you say HWS will be some WH HWS. Right? So this will be again in the dual vector space, in the dual H star. W is again should be thought of as an element of H star. Huh? Okay. But okay, that's just a more abstract way of saying it. But here it is. Here I've just chosen a basis. So with respect to that basis is that W1 and W2. Okay. So given that, once I do this, then of course we know that automatically this condition is satisfied, right, because of this commutation relation. And then I can start applying the lowering operator. Right? But again, I don't need to apply all the possible lowering operators. Lowering operators are E minus alpha 1, E minus alpha 2, E minus alpha 3. These are the 3 lowering operators, right? Because the negative roots. These were the negative roots. But again, you see that E minus alpha 1 with E minus alpha 2 is again some number times E minus alpha 3. I will use this symbol here because the number, that's not an important number. The important thing is that the number is not 0. That's the important thing. So this commutator is that. So therefore, I don't need to apply E minus alpha 3. I can just apply E minus alpha 1 and E minus alpha 2 in all possible orders. You have to remember the orders are important because they're not commuting. E minus alpha 1 and E minus alpha 2 do not commute, right? So you choose all possible orderings, but you need to only apply E minus alpha 1 and E minus And that way you construct all the other states of the representation. Okay? Yeah. And what else we know then? Okay, if I look at this equation, so this tells me that as far as this guy is concerned, this SU2 subalgebra is concerned, it must be so suppose I just apply E minus alpha 1s, and I don't do anything, I don't touch E minus alpha 2 at all. I just apply E minus alpha 1. Okay? Then this eigenvalues W1 will start decreasing in units of 2, right? Again, this has to do with the normalization, because with the SU2 we saw that it was decreasing by unit of 1, but here we have doubled the eigenvalue, so decreasing by units of 2. So you will get W1. So if I start applying, so let me write it down here. So if I apply R E minus alpha 1 on this state, okay, then we know. So this okay. Of course, we can say more things, but let's focus on just this SU2 subalgebra. Just focus on that. Of course, we have to also consider the other one, E minus alpha 2 also. But let's, for the moment, focus on this. So start applying this here. This will now, as far as this first H1 eigenvalue, RH1 of this guy, on acting on this state, will be the eigenvalue W1, which is already there, plus minus 2. Right? Because it's going to decrease the H1 eigenvalue in unit minus 2 times this state again. And so on. Finally, looking at this, we know that since its highest weight is W1 for this SU2 subalgebra, you will go all the way up to minus W1 and stop there. That will be the lowest weight state. Right? So from W1, you started with W1, then you will have W1 minus 2, etc., all the way up to minus W1. By just using this SU2 subalgebra. Okay, so this is one thing. So you see, so let me just write it in the following way. So I start with the W1, W2. Now I apply E minus alpha 1. I will not use R. It's understood that it's in that representation. It's R of E minus alpha 1. But just to avoid writing too much, I will just do that. So this is going to give me, as far as W1 is concerned, this is going to be W1 minus 2. But what about W2? You see, again I erase that. This one had this was, remember what was it? It was 2 comma minus 1. Sorry, E alpha 1 was in our notation, it was 2 comma minus 1. This was the H1 eigenvalue and this was H2 eigenvalue. So E minus alpha 1 will have eigenvalue minus 2 comma 1. So when you apply E minus alpha 1, of course W1 shifts by minus 2, right? But W2 also shifts to W2 plus 1, the plus 1 from here. Okay? But okay, I'm not focusing on that, I'm just looking at this object. And so on, you keep going, and finally you will get W1 minus W1 all the way after some steps, and there will be something in the second one. Okay. So the number of steps is required is how much? 2W1, 2W1, right? No, W1, so W1 steps, right? So every time it reduces by 1, so W1 steps, so you will get W2 plus W1. This chain. See, every time you apply once, you reduce by minus. Then you have to apply W1 times that to make it minus W1. So there is a, so you will see that if a W1 exists, you should also go up to minus W1 there.
Professor, okay, this relation, well, we got it from SU2 when we know that from J to negative J, but this relation was actually derived upon the fact that we decrease or increase by only one. It was a summation of J minus Q.
Yeah.
But here we didn't do this relation here, and it also decreases by 2. So how would we know that it is from W1 to negative W1? Maybe it is something in between or
No. I mean, this is a matter of simply rescaling. I mean, we just rescaled, right? Instead of sigma 3 by 2. So when you have sigma 3 by 2, you can start with some j, right? But this j could be half integer also, right? But now we are saying because I'm going to multiply everything by 2. So this is 2j. Yeah. So that's why this is always integer for this normalization. If sigma 3 by 2 is eigenvalue j, then clearly 2 sigma 3 by 2 is eigenvalue 2j, right? So therefore these are all integers. And when you had sigma 3 by 2, then what was happening? The moment you apply E minus, you will get j minus 1. Right?
It's like we're replacing j by 2j.
2j, exactly.
Yeah.
It is, I mean, it's more convenient because we never have to work with the half integers, no? So it's more easy to count. Except that you have to remember that jump is in units of 2. As far as the H1 eigenvalue is concerned. But H2 eigenvalue here is increasing by one unit. W2 versus W2 plus 1. That is because E minus alpha 1 had the eigenvalues minus 2, 1. So let us now do, okay, this was that. No? But now you have to also at the same time apply E minus alpha 2. If I apply E minus alpha 2, what am I going to get? E minus alpha 2 had the charge 1, I mean the eigenvalues 1 minus 2. Okay. So you're going to get now W1 plus 1, comma W2 minus 2. And so on. You keep going up. Okay. Anytime this number is, now we applied this here. If this number is not 0, which of course is not 0 if W1 is non-negative, so this is certainly not 0, then you can also apply E minus alpha 1 again on that, right? So they say you have to go in 2 directions, right? Because you have to, before in SU2, it was just one line, right? So you started from there, you just apply E minuses, and you keep coming back, and until you hit the lowest state, right? But now we are in a 2-dimensional plane, okay? So you have to start applying both in various orders. For example, I come here, so what is the weight here? What is the weight here? This will reduce the units by minus 2. So W1 plus 1 minus 2, so W1 minus 1. And maybe W1 minus 1, comma, this one is going to increase by 1 unit, so W2 minus 1. Okay. On the other hand, now from here, again I have to apply E minus alpha 2. So you see that you again come to the same idea, because now I have to add the weights of this. So W1 minus 2 plus 1 is W1 minus 1. W2 plus 1 minus 2 is that. So first question you can ask, I mean, there are 2 ways of getting here. There is one way and there is another way. How do I know? Is it the same state? Maybe there's a degeneracy. In SU2 case, we saw that for every weight, there was no degeneracy. There was only one state. There was always one dimension. But here I find these 2 states. Is it possible that they are actually not linearly independent? That actually one state is some number times other state? When I come this way, maybe just you get again the same state as that up to some overall number, right? That could have happened. In which case it will be one-dimensional. This space will be one-dimensional, right? But if they are linearly independent, these are 2 independent states, so it will be 2-dimensional. There will be degeneracy. So this is the new complication that you find. The moment you go beyond 1 dimension. I mean, here the Cartan space was 1 dimension. Now here the Cartan space is 2-dimensional. Cartan subalgebra. No? So you have this issue. You have to check. Every time you have to check whether this is linearly independent or they are the same. So this keeps going. No? It keeps going. There are these chains like that. No? This is the E minus alpha 2 chain. This is E minus alpha 1 chain. and there are mixed chains, and so on and so forth. So it becomes pretty complicated in general to discuss that. But let me just take some simple examples, which are the representations of small representations, and work it out. Sorry, these things are not in the notes. Huh? I mean, the way I am presenting it is very different from what is in the notes. So, but I hope the recording is reasonable that you can follow it again at home. Okay, so let's take a simple example. Say, let's suppose W1, W2 is 1, 0. I think that's clearly as the numbers become large, it's going to become higher and higher dimensional, right? So one should start looking at the small numbers. So let's take, okay, 0, 0 is trivial. W1, W2 is 0, 0. That's the easiest one. That's nothing happens. I mean, this singlet, this is just one-dimensional representation. Okay. This is a one-dimensional representation. I mean, meaning that when you apply E minus alpha 1 or E minus alpha 2, every time it is 0. Right? It is 0 because if I apply E minus alpha 1, so to see this, if I start from 0, 0 and apply E minus alpha 1, I'm going to get here minus 2, comma 1. But how can there be minus 2? I mean, look at the SU2, this SU2, first SU2. I mean, this is 0, how can you have minus 2? No? This is the highest weight. Because in SU2, you know, if the highest weight starts from 0 up to minus 0, which is 0, that's it. No? So this cannot be. So this should annihilate it. This will give you 0 times. No, this will give you annihilated. R E minus alpha 1, and similarly alpha 2, both of them will just give you 0, acting on this state. No? So that's a singlet, no, nothing happens. So the the simplest example is this one. Either this or 0, 1. These are the two. So let's look at one of them. So I start with this 1, 0. Now I apply E minus alpha 1. So I will get here minus 1, comma 1, right? Because again, you keep using that, minus 2, 1, and then, now look at this, that's it. This was when you say 1, it means in the SU2 normalization, it is spin half, right? So this is a doublet. So this is the doublet as far as that SU2 is concerned, it stops here. If I had continued here, I'm going to get a minus 3, comma something, comma. But there is no 3, I mean, there should be, for every eigenvalue here, there should be a negative. But not, you know, if there was a minus 3, there should have been a plus 3. No? So that cannot happen. So it stops here, because it's a doublet, so that stops here. But here, this was a singlet, because it was from the second SU2 point of view. I mean, now, so there are two SU2, I keep focusing on these two SU2s. This SU2 and that SU2. So now I did the first SU2, that's what I get. Now I apply the second SU2. So E minus alpha 2. That cannot be because it's a singlet of the second SU2. So nothing cannot give, it should give you 0 there. But this is not. This is 1, which means in our old normalization it is spin half. It has doublet. So I should get E minus alpha 2. If I apply E minus alpha 2, I'm going to get, this will be minus 1, and that will be 0. That's it. There's nothing else. So it's a three-dimensional representation. Now, yeah. I mean, again, you see, this is 0. Now, I think last time somebody asked, why not? I mean, why can't I just apply E minus alpha 1 on this? No? I mean, how do I know that this should annihilate it? One way to understand is that if I had done that, I would get a minus 2 here. I mean, again, you see, with respect to E minus alpha 1, if this does not annihilate, then an E plus alpha 1 should also not annihilate it. I mean, so that you would get a triplet representation, for example. No? I mean, again, for SU2, you remember, I mean, from the first SU2 point of view, if I look at the eigenvalue, some eigenvalue here, 0, then how can be, either it's a singlet, or if it's not a singlet, so suppose I have a minus 2 here, then I should have also a plus 2, right? Or if I have a minus 4 here, I should have also a plus 4. Otherwise, it's not a representation of SU2. Okay. So, if this exists, then that must also exist, which will be plus 2 and something here. Okay. This I'm not interested in right now. I'm just looking at this SU2. So I'm not interested in the second number. But this cannot exist. So the question is, does it exist? Huh? And that you can see in the following way. So I look at E minus alpha 2. So what is this state? This state is E minus alpha 2, E minus alpha 1 acting on 1, 0. That is the state here. And now I apply E alpha 1. Okay. I apply E alpha 1. So so let's see, again, this is all understood that there's an R here, representation, but I will, for the writing simplicity, I'll just write like that. Now let us start moving this across, because I know if I can move alpha 1 all the way here, it annihilates it, right? This is the highest weight state. So let's start moving it up. So when I move it across here, this commutes. E alpha 1 with E minus alpha 2 is 0. You can check in that this was one of the zeros. So I can move this across. So I get here E alpha 1. Okay. Alpha 1 with alpha minus 1, when I move it, I try to move it further, but I'm going to get a commutator. When the term where E alpha 1 is sitting here, that annihilates it. So from here, you get basically H1. I mean H1. You get H1 here. Okay. H1 acting on that is some number. So 1. So you get basically E minus alpha 2 acting on 1, 0, up to some number. Okay. But we already argued that E minus alpha 2 acting on that is 0. I mean, this is the original state. E minus alpha 2 acting on that. This is acting on, if this was not 0, then I would get this state here. But we know that this is 0 because it's a singlet. No? So that's why this doesn't exist. This doesn't exist. Also that doesn't exist. Doesn't exist meaning it annihilates it. If I apply E plus alpha 1, it just gives you 0. Therefore, E minus alpha 1 should also give you 0. From that SU2 point of view. See, this, you are just looking at this SU2. The knowledge of SU2 is very useful in all of this algebras. For every state, I mean, if you look at, focus on one SU2, it should be a representation. It should be one of the spin J representations that we talked about. So this is the idea. Okay, that's a three-dimensional representation. In fact, this is nothing else, but it's a defining representation. Because defining representation was the defining representation was just that. H1 was 1 minus 1, 0. And H2 was 0, 1, minus 1, 0, 0. And now if you look at the action of this on the state, let's say 1, 0, 0. So I look at this thing. So what are the weights? What are the eigenvalues? I apply this. So this gives me 1, right? You just multiply this matrix to that column vector. You'll get the same column vector times 1, right? When you multiply here, this gives you 0. So H1, H2 for this state, so for 1, 0, 0 state, H1, H2 gives you the eigenvalue. So W1, W2, what equal to is 1, 0. I mean 1 for this and 0 for that. So that is the state, original state here, right? Now apply, so now look at the next state. So you have 0, so look at now, can I erase this? And I look at now this state, here, second state, 0, 1, 0, 0, 1, 0. So now what do we get? So if I multiply, I'm going to get minus 1, right? So this will be minus 1, 0, 1, 0. And when I multiply here, I'm going to get 1 times 0, 1, 0. So this state has eigenvalues. W1, W2 is minus 1, comma 1. That's that state. Okay. And finally, the last state here, the last eigenstate here is 0, applied now on 0, 0, 1. Okay. Now I'm going to get 0 here, because this is 0, whereas here I'm going to get minus 1. So this is minus 1, 0, 1. That is, so this state has eigenvalue 0, minus 1. So that's that state here. Okay. So this in the defining representation, the 3 weights are exactly these 3 weights. And also you can see the first one, this one was the highest weight because it is annihilated by E alpha 1. E alpha 1 was 0, 1, 0, 0, 0, 0. So that clearly annihilates that, right? And E alpha 2 was 0, 0, 0, 0, 0, 1, 0, 0, 0. So that also annihilates it. So this state, this vector is indeed the highest weight in our original defining representation. And then we applied E minus alpha 1. E minus alpha 1 would be exactly the transpose of this one. So when I apply on this, I will get that, which had indeed the weight minus 1, 1, which is that one. And then on this state, I apply E minus alpha 2, so which is the transpose of this here, then I will get that state, 0, minus 1. So these 3 weights are just the defining representation. I mean, defining the way we define the SU2 algebra itself, that's defining representation. But, okay, any question here? Just before I continue.
Can we go back to the original state?
Yeah. You can apply, just go backwards. Yeah, you can. Actually, you can even directly go from here to there by applying E alpha 3.
Yeah.
No? But what we are doing is we are not using alpha 3 at all. We are only using alpha. Because otherwise, you can have, when you start looking at more complicated examples, if you also allow alpha 3s, then there are many different routes to get there. No? So this issue of multiplicities becomes even more complicated. But the point is that E alpha 3, I'm not generating anything new. Because E alpha 3 is a commutator of E alpha 1 and E alpha 2.
E alpha 3 or negative, or E negative plus 3?
No, okay, so from here, if I go, I have to go positive, right?
Yeah.
If I want to come this way, then E minus alpha 3. Yeah, you can always reverse the path also. You can just directly reverse the path because now if you apply E alpha 2 on that, then that is the same as applying E alpha 2, E minus alpha 2 on this state, right?
So it is the other way.
Yeah, exactly. So you can just go backwards. E alpha 2 apply there, then E alpha 1 you go backwards. But in that process, you don't get another state. I mean, so if I apply E alpha 2 on this, of course, the eigenvalues will be there. You can ask the question, is it the same as original state or linearly independent state? No? But what I'm saying is it is not a linearly independent state because this state by definition was E minus alpha 2, I mean this state, 0, minus 1 state, was by definition E minus alpha 2 acting on this state. Right? That's how we got it. Now, what I want to do is I want to apply E alpha 2 on this. So I'll get here alpha 2, which is the same as alpha 2 there. But then you can commute E alpha 2. You get H2. H2 is just going to give me a number. And the E alpha 2, the second term of the E alpha 2 comes here, it annihilates it. So it is some number times this state. So it's not some new state, it's the same state. No? It's not a linearly independent state. Okay. If not, now let me see. There is another, if you look at this diagram, it is not very, if I plot it in the original, the lambda 8, H1 eigenvalues thing, then in this picture, the roots were something like this here, I mean, this is 60 degrees, I don't know. These were the roots. Now, if I plot in this picture with this lambda 8, here remember this is eigenvalues h1 and h2. So, in order to go from h2 to lambda 8, you have to do something, and some h2 you have to subtract some number times h1. No? And then the root 3 is floating around and so on. You remember the relation? There was some, yeah, you can easily work out the relation. There are some root 3s and some combination of h2 and h1 will be the lambda 8. So in this case, what happens is that this state, 1, 0 state, is somewhere here. It's actually at 30 degrees here. This is 60 degrees, 30 degrees here, this state. And then when you apply E minus alpha 1, this is going to move here. So this is the state what we call 1, 0. This is the state minus 1, 1. And finally, when you apply, remember this is alpha 1 and that's alpha 2. So when I apply x minus alpha 1, it is just you add these two vectors, right? Because minus alpha 1 is that. No? You just add these two vectors, the result will be something here. There will be some parallelogram, you draw that. Okay? And then finally, when you apply minus alpha 2, it is adding this vector to that vector, and you will end up here. It is basically maybe somewhere here, something like that. Right? And you will see again, all the lengths are the same. Lengths are the same because again our normalization for the lambda, trace lambda A, lambda B was some number delta times delta A, right? For that reason, it's all very nice pictures, very nice geometric pictures up here. So okay, this is the 0, 0 minus 1. Okay, this picture is a little different from the, let's say, forget the fundamental representation. Just look at the original adjoint representation. This adjoint representation, it was completely symmetric. You see, the reflection symmetry. If you reflect along this axis, meaning perpendicular to one of the roots, this is symmetric, or perpendicular to that root. If you do that, again it is symmetric. This picture is not symmetric, right? Because if that symmetry is still there. But this is not completely symmetric in the sense that, I mean, for this vector, there is no opposite vector, unlike here. Unlike the roots, we have this line, there's a negative of that. There's this line, there's a negative of that. Here, you don't have that. The negative of that would be here, right? But that is not there in this, it's not a weight in this. Okay? So that is where, so there is another representation. There is another representation that is another three-dimensional representation. And that is the one which starts from 0, 1. So let me erase this part here. You see, we started from 1, 0. If I go to the the negative of that, this is going to be 0, 1. Right? Here, these eigenvalues are 0 and minus 1. If I just go to the negative, it will be 0, 1. Okay? That's another possible highest weight we could have chosen, right? Which we haven't done that so far. But now let's look at 0, 1. If I had started from 0, 1, so now my highest weight is the 0, 1. So I start with the 0, 1. Now what can I apply? You see, with respect to the first SU2, I mean this SU2, because H1 is 0, this is a singlet. Right? I mean, remember, there in the other case that we did before, we said this is 0, so E minus alpha 2 annihilates it. It gives you 0. Right? And E minus alpha 1 will certainly not give you 0 because this is doublet representation. So it will give you minus 1, 1, right? That was the other what we did before. I mean, here's the picture, right? 1, 0, we said, if I apply E minus alpha 2 on this has to be 0 because as far as the second SU2, the second SU2 labeled by 2, this is a singlet, is a 0 spin. So both plus alpha 2 and minus alpha 2 should annihilate it. No? Okay. Here is the other way around. It's the E minus, I mean, in this case, it's the other way around. In this case, E minus alpha 1 annihilates it. This gives you 0 because it's a spin 0 representation of the first SU2. But when I apply E minus alpha 1, alpha 2, this is not 0 because it's a doublet. This is spin half with respect to the second SU2. Right? Spin half. So it should give you, so this will give me, this remember has weights 1 minus 2, this guy. So I add that up. So I will get here 1 minus 1. 1 minus 1, right? Now, that's it. If I further apply E minus alpha 2, it should be 0 because it's a doublet. Right? This should be the lowest weight of E minus alpha 2. Now I apply E minus alpha 1 because now you see this is not a singlet of the first SU2. This is spin half. So it's a doublet. So when I apply E minus alpha 1, I will get here, this is charge weights minus 2, 1. So I'm going to get here minus 1, 0. So these are the weights. These are the weights of this representation. Now, if you look at this picture here, that was so the weights are 0, 1. 0, 1 is exactly the opposite of that. So maybe I should put a cross here. So initial the defining representation had these weights, circles. Okay. But now you see the highest weight of this other representation is this one, cross. And then you have 1 minus 1. 1 minus 1 is exactly the opposite of that. So it will be diametrically opposite. It will be here. Oh, this is a cross. And finally, you have minus 1, 0, which is the opposite sign. So it will be diametrically opposite here. This here. So the previous one was giving this triangle. Now this representation is giving this triangle. Okay. So these are the two, both are three-dimensional representation. Okay. But the difference between this representation and that representation is that the weights of these guys are exactly the negatives of the weights of that guy. We just take the minuses of this. Okay. And now, does that remind you of something that we discussed in the SU2 case? When the eigenvalues are all change the sign. That is a complex conjugate representation. Yeah? So this, so usually in physics literature, we call this representation triplet, because there are 3 states. So this is denoted by 3. Right? This one is denoted as a complex conjugate representation. So 3 star. 2. Unlike SU2, in SU2, remember when you did the complex conjugate representation, we said that it is just a similarity transformation. It's the same representation as the original one. Okay? In SU2. Why is that so? Because in SU2, in every representation of SU2, every eigenvalue of H, which is some integer or half integer, there's also a negative of that in the given representation, right? So when you change the signs, nothing happens. You just change the basis of the states. It's just renaming the states. No? Here it is not. I mean, the eigenvalues are changing. These eigenvalues are not the same as that. So this is not a similarity transformation. These are really 2 different representations. Okay, that's one thing. And now let's take another example. Let's take 2, 0. Let's take a 2, 0. Sorry, maybe I should stop a little bit because these are not in the notes. So maybe you would like to take the notes and note it down. Yeah, I wanted to tell you that this discussion that I'm making today is not in the notes. So you'll have to really go through again these lectures later. Okay. Can I? Maybe.
Professor, the SU2 can be spin 0, can be spin half, and can also be spin 1.
Repeat again.
The SU2
For SU2?
can be single, doublet, and also triplet.
SU2 any spin j. For a spin j, the dimension of the representation is 2j plus 1, right? So if you take j equal to 1, that is dimension is 3, so that's a triplet. If you take j equal to 3 half, it's a 4-dimensional representation. So any dimension you can have. Yeah. Any dimension, actually for any integer dimension, you have a spin. Just 2j plus 1 should just set 2j plus 1 equal to that number. And the solution will be j will be some half integer or half integer. So yeah, for every dimension there is a representation, irreducible representation. Yeah, that happens. So now we'll start going to something slightly more, the next complicated one. Here it was 1, 0, 0, 1. This was very easy. So let's go to 2, 0. Okay. And 1, 1, and so on. Let's go to that. Then. So, okay, 2, 0. Maybe I should note it down somewhere, otherwise we'll forget. So what we had was for the fundamental representation, it was so there's a 3 representation. The weights were 1, 0, 1, 0, and minus 1, 1, and 0 minus 1. Right? These were the 3 weights. And for the 3 bar, we have here 3 bar representation. These are weights, 0, 1, 1 minus 1, and 0, 1, and minus 1, 0. These were the recommendations. So now let's look at 2, 0. So let's look at the 2, 0. So highest weight state is a 2, 0 state. So 2, 0, so we start from the 2, 0. Now, by looking at this, we see immediately that with respect to the second SU2, it's a singlet. No? A 0, so a singlet. With respect to first SU2, it's a triplet. The j equal to 1, 2 divided. So it's a triplet. So therefore, I can apply 3 steps. E minus alpha 1. So this will give me 0, 1. I mean, somewhere I should note it down. The E alpha, because these are the important things. So E minus alpha 1 has weight minus 2, comma 1. And E minus alpha 2 has weight 1 minus 2. So that, yeah. So I just add the weight of that E minus alpha 1, so you get that. But now it cannot stop here because this is a triplet, so I can go one more step. And after that I should stop because the triplet, so this is the lowest weight for this SU2. So here we'll get a minus 2, comma 2. Okay. And now let's look at the second SU2. Second SU2, of course, we said it is a singlet, so nothing happens there. But here it is not a singlet anymore. Here it's a doublet, the spin half. So when I apply E minus alpha 2, I'm going to get minus 1, 1. And that's it. It should stop there because it's a doublet from this for this. Now here, if you look at that, this one is a triplet of the E minus alpha 2. I mean the second SU2. So I'm going to get here minus 2, so I add that, so you get here minus 1, 0. And then one more step, because a triplet, so I should go one more step. So I'm going to get here minus 2 and 0. Now what about here? If I apply E minus alpha 1, you see this is it's a doublet of the E minus of this first S1 SU because it's S1. So it comes here. In fact, you can check. If you add this to that, you get that. And that's it. This stops here. I mean, it's a doublet, so it just stops there. So this is a 6-dimensional representation. This is a 6-dimensional representation. Right. So again, you see this is it's a triangle. I mean, if you had drawn it in this H1 lambda 8 plane, you would see that. Yeah, you would see something like this here. So first of all, 2, 0 is just the double of this line, so it comes somewhere there. But now I don't know what symbol I should use. We have a cross and then this. So double circle, let's say, double circle. Then this is also a way to the double of that. You see the 0, 1 happens to be also here. So this is also part of this double 0. And then another one, which is the double of this. You see, minus 2, 2 is simply the double of minus 1, 1. So this will be an extension of this line. So it comes here somewhere. It's a double line, double circle. So this formed a triplet of alpha 1. This double circle, that double circle formed a triplet of alpha 1. And then, so this one is here. And then similarly, you'll have this state, 1 minus 1. You see, 1 minus 1 appeared there. And minus 1, 0 also appeared there. So these are also double circles here. And finally, there is a last one is 0 minus 2, which is double of that. So it comes here. There's again like a triangle here. Okay. But so you see that, I mean, these weights, these 3 weights already appear here. These are these 3 weights. Okay? But now it's in a different representation. Here, you see, this is not, in this representation, this is not a highest weight state. In this representation, this is the highest weight state.
Can we choose the highest weight state as we like?
Exactly. Any numbers. Any integers. I mean, we said that any integers. Just choose any W1 and W2. Which are the only condition is that these are W1 and W2 are non-negative integers. Non-negative. For every one of them, there is a representation. This is the only condition. And actually, all the irreducible representations of the C3 are labeled by these 2 integers. Just like for SU2 is labeled by spin J. No? Okay, here it's just labeled by SU3 is labeled by these 2 integers. You specify these integers, there's a unique irreducible representation. That is the statement here. Okay. I mean, this fact is not surprising, right? I mean, after all, even in SU2, we saw that. I mean, if I look at the spin 1 representation, I have +1, 0, and -1. Where this guy is the highest weight, that's the lowest weight. If I had chosen, again, draw a spin 2 representation, I have +2, +1, 0, -1, and -2. So you see, these weights are appearing also in spin 2 representation. Same weights, except that this weight is not the highest weight state. J plus acting on that is not 0, it gives you that. Whereas here, J plus acting on that gives you 0. Right? So this is not surprising that the same weights which were appearing in the 3 bar is also appearing in this representation. It's called 6-dimensional representation. Not surprising. You can do the same thing now. This was for 2, 0. You can do it for 0, 2. Okay, you do it for 0, 2. Picture is again a 6-dimensional representation, but it will be just like the 1, 0 and 0, 0, 1 and 1, 0, where these triangles were just reflected. The same way, you get here again a 6-dimensional representation, but it will be the complex conjugate representation. Okay. So that is fine. Now, okay. Now here you see, again you can ask questions about the multiplicities. No? We said, let's go back to this picture here. If I look at this state, or even let's see, yeah, I mean if you look at this state, I have two ways of reaching it, right? I could go in this sequence, or I could go here, here, here. Okay? Now you have to, again, you immediately ask the question, are they linearly, are they two different states, two independent states, or they are the same states? No? That's a natural question to ask. In this case, you don't have to work hard, because we see in all of these things there is a symmetry that if you look at this doublet, I mean here I know there is only one way to reach. No? So this I know multiplicity is 1. It's not possible. It cannot be 2. But the number of states here must be equal to the number of states there, because this is an SU2 representation with respect to the first SU2. No? So the multiplicity here cannot be different. It has to be 1. So this argument shows that if you come this way or if you come that way, the states that you get is exactly the same state. Up to some number, but they're not they are linearly dependent. They're not two independent states. And you can verify that. You can check it. But let me go to some example. Okay, we'll come back to this. I hope I can come back to that. Okay, let's look at, okay, what is other complicated, I mean, so we have done 1, 0, 0, 1, we have done 2, 0, 2, 0 and 0, 2. I didn't do it, but you'll see that it's just the reflection of that. What about 1, 1? 1, 1 you already know, because that's the adjoint representation. If you look at the adjoint representation, which was there was a alpha 3, E alpha 3, that was 1, 1. The weights were 1, 1. And then there was a 2 minus 1, alpha 1, and alpha 2. This was minus 1, right? And then the negative ones. But you see that if you look at this representation, according to our definition, this is the highest weight state. Because this guy is evaluated by both alpha 1 and alpha 2. Right? Because you see, in the adjoint of in the representation, alpha 1, alpha 3 is the same as E alpha 1, E alpha 3 commutator. But this commutator would be 0, because if it was not 0, the sum of these two must have been a root, but it's not, so therefore that is 0. Right? And the same thing with alpha 2. If you look at alpha 2 here, commutator with alpha 2, alpha 3, if this was not 0, then you should have something there. But that is not there, no? So this is 0. Or you can check explicitly, of course. You know the matrices, you can check. So these are 0. So this is the highest weight of the adjoint representation. Okay, 1, 1. Not this or that. This is the adjoint highest weight. So the 1, 1 highest weight state equal to 1, 1. This is nothing else but the adjoint representation. So it's a-dimensional representation, because adjoint representation is a-dimensional. This one itself, if you take the complex conjugate, is the same, right? Because in this picture, you see, if you take the negatives of these guys, they are also roots, right? So this is an example where it just up to similarity transformation is the same representation. Huh? It's just relabeling the states. So this is it's a pseudo-real representation.
So 2, 0 was the 6th-dimensional representation.
2, 0?
2, 0.
Is the six-dimensional representation. Yeah, this was 2, 0. This representation was 6-dimensional, and 0, 2 was 6-bar complex conjugate. So in this case, we didn't have to really calculate to check whether these two ways of getting it, you get two different states or not. Huh? Because we have other ways of deciding that it has to be one. Huh? But let us take some example Now, here already, you see in the adjoint, you already see the situation. If I follow the same procedure that we did, this is my highest weight. I apply E minus alpha 1, I get here. I mean, this is a doublet of the first SU2, right, because it's spin half. So it can only be, you only can apply once. Second time it should give you nothing. No? When you apply E minus alpha 2, you get here from there, no? Again, this is a doublet of the second SU2. So it stops there. Okay. But now this is a triplet of the first SU2 because it's spin 1. So you apply 2 times E minus alpha 1 and then E minus alpha 1. And you get here minus 2, 1. Okay. From here again, if you apply E minus alpha 2, I mean this again, you see this tells you that it's a spin 1 triplet of the second SU2. No? So once and again once. So this one you get 1 minus 2. And finally from here, again it's a doublet, so you come here and you get minus 1, minus 1. Okay, so this is all. But here you see already that if you come this way or if you come that way, here, this is actually the states that you get are linearly independent. You see, why? Because we already know, this is the joint representation, we already know the Cartan space, subspace, which is the weight 0, 0, right? That's 2-dimensional. Okay. So this is indeed, there are 2 linearly independent states. So in other words, what I'm saying is that if I apply E minus alpha 1, E minus alpha 2 on the 1, 1 state, this is not the same, this is not the same as other way, E minus alpha 2, E minus alpha 1, acting on 1, 1 state. These 2 states are linearly independent. This we knew because we constructed the joint representation. But suppose you didn't know about it. Right? Somebody has just said, okay, can you please construct with the 1, 1 highest weight. Right? So like we were following the other procedure, we will just do this diagram. No? And then we arrive here and we say, okay, we ask the question, how many states are there now? No? Can we prove that these 2 states are linearly independent? No? That's the question we want to ask. And this you can prove. Let's try to prove that here. Let's try. So if it is linearly dependent, if it's not linearly independent, then that means there must exist some numbers such that when I take the linear combination, some linear combination must vanish, right? So if these 2 states, let's call it I don't know. If these 2 states were not linearly independent, then there must exist some numbers, let's say x and y, okay, some numbers, maybe even complex numbers, doesn't matter, some complex numbers, such that x times E minus alpha 2, E minus alpha 1 acting on 1, 1 plus y times E minus alpha 1, E minus alpha 2 acting on 1, 1 is equal to 0. I mean, that's a definition that they are not linearly independent, right? On the other hand, if you see that the only way to satisfy this equation is that x has to be equal to 0 and y has to be equal to 0, then you conclude that these 2 states are linearly independent, right? So that's what we want to check. Okay, so let's assume that they are not linearly independent. So this equation is true. Let's assume that. Huh? Then we come to some contradiction. So let's see, if this is true, then if I apply E alpha 2 on that should also be vanishing, right? Because if this state itself is 0, I mean, if we are saying that if this state is 0 state, I mean, when I say 0, I mean it's a 0, it's a null state. If this state is a null state, then any operator acting on that will be still 0. right? So in particular, if I apply E alpha 2 on that, it should be 0. So let's see what happens. If I apply on this, so we have to do some steps here. So we need to use some commutation relations here. So E alpha 2 with E minus alpha 2 is nothing else but H2. So idea is again always the same. Since this is the positive root, right? Alpha 2 is a positive root, and we have defined this thing as a highest weight state. So if I can push alpha 2 E alpha 2 all the way there to the rightmost position, it will annihilate it. No, it will annihilate this state. I mean, by definition, E alpha 2 acting on 1 1 equal to E alpha 1 acting on 1 1 equal to 0, because that was the definition of the highest weight. So then I can systematically start pushing it to the right. No? In doing so, I will pick up the commutators. Right? So here I will get 2 commutators. First, when you commute with that, so that's going to give me H2. Right? H2 acting on E minus alpha 1 1 1. Okay? Plus another term which will be E alpha 1 will be here. Sorry, E alpha 2 will be there. Right? I mean, plus another term which will be E minus alpha 2, E alpha 2, E minus alpha 1, 1, 1. Right? That's the first term. But this is fine because we know that E alpha 2 commutes with E minus alpha 1. Okay? So you can move this without costing any commutator, and then E alpha 2 annihilates it. So this vanishes. Okay? That's the first term. Second term, so plus y. Now I'm applying E alpha 2. So E alpha 2 commutes with E minus alpha 1. So already I can move it there. And then you just get H2. So this gives you E minus alpha 1, H2 acting on 1 1 equal to 0. That's one equation, right? So that's equal to 1. We are saying that if this is 0, then E alpha 2 acting on it is 0. So what is this? Now H2, what is H2 of this? When I apply E minus alpha 1, we get, we get minus 1, 2. So this state has eigenvalue minus 1, 2. Right? So H2 picks up the second entry. So this is 2. This is 2 times E minus alpha 1, 1, 1. Right? And here H2 is just 1. Right? H2 acting on that is simply 1. So this is just 1 here. This is simply 1 times H1, 1. So combining these two, you see, both the states are of the same type, E minus alpha 1 acting on 1, 1, E minus alpha 1 acting on 1, 1. But the coefficient is 2x plus y. Okay? So this applying this here, so where can I write it now? Okay, I can erase this. So the result of this thing is that 2x plus y E minus alpha 1, 1, 1 is 0. Okay? That's one. So if you are saying that if this is true, then 2x plus y must times this 0. However, this state is not 0 because that is this state. This state is certainly not 0. E minus alpha 1 acting on that, because this cannot be 0, otherwise this would not be a doublet under the first SU2. Okay? So this conclusion, conclusion is 2x plus y must be equal to 0. Okay, that's one thing. But still we are not done, because we have just applied E alpha 2 on this. What if I apply E alpha 1 on this? After all, that is, right? If this is 0, E alpha 1 should also give you 0. No? So now let's apply E alpha 1 on this. So let's apply E alpha 1. Now, so alpha 1 of course commutes with that, E minus alpha 2. So I can already push it there. And then when you take the commutator of that, I will get H1. Right? And then, okay, so the first term gives you just 1 times x, E minus alpha 2, 1, 1. That's the first term. Is that clear? And I'm repeating the same step. Exactly the same step as before. So again, so this I can move it across here because it commutes. Then I commute with that. there will be one term where E alpha 1 comes here, but that is 0 because highest weight. So the only contribution is from the commutator, but that gives me H1, and the eigenvalue of H1 is 1. So you get the second term. When I apply alpha 1 on this, so you take the commutator, so you get here y, H1, E minus alpha 2, that's the first term, plus then I will have a term which will be E minus alpha 1, E alpha 1, and E minus alpha 2, acting on 1, 1. So this whole thing acting on 1, 1. Again, this term is 0 because this commutes, so I can move it there. It annihilates it. So this guy goes out. Okay. So now I have to just look at action of H1 on this state, E minus alpha 2, 1, 1. But E minus alpha 2, 1, 1 is this state. Right? So 1, 1, E minus alpha 2 is that with these weights. So, H1 acting on that is 2. Right? So here you get 2. 2 times E minus alpha 2. So this gives you E minus alpha 2, 1, 1, and x plus 2y. Okay. Again, we know this state is not 0, because that cannot be 0. This is a doublet with respect to second SU2. This cannot be 0. So therefore, x plus 2y is 0. Is impossible, right? I mean, this tells me y is equal to minus 2x. Substitute that here. So this becomes x minus 4x, which is equal to minus 3x. So therefore, if this is 0, then it implies x is 0, and it implies y is 0. Okay. So this says that
They are linear.
they are linear. So it's two-dimensional. We knew it. I mean, I'm just trying to do it we knew it because we knew exactly what is the joint representation. I mean, that's how we started. But this proves that. Let me see what else I can do. Okay, maybe I should do the tensor product representations tomorrow, because now it's too late to start something different. Maybe I can just give you one more example, and then one more example. Something a little bit more complicated. Yeah, okay, let's see. So this, I will draw another one. So let's start with the highest weight. Highest weight 2, 0, let's see. That's an easy one. 2, 0 we did already. 2, 0 we did, 1, 0. So everything with the sum of the two numbers equal to 2 we have done. So now we have to go to sum equal to 3. No? So let's take 2, 1. 2, 1. 2, 1, the picture is more more complicated. So I start with the 2, 1, my highest weight state. So you can immediately see that this is a triplet with respect to alpha 1, E minus alpha, the first SU2, and the doublet with respect to the second SU2. So here I get here E minus alpha 1, so 2, 1. E minus alpha 1 is minus 2, 1. So 0, 2. And next one, again, minus alpha 1 is minus 2, 3. Okay, now it stops here because we know this is a triplet, so it cannot continue further. Now, if you look at another, this is a doublet, so I can apply 1 E minus alpha 2, and that's it. And this time I will get here minus 1, 3. Now, from these two numbers, from this number, I know it should be a triplet with respect to the second SU2. Right? This direction, I should go. There should be a triplet. This one, this gives you 3. This means spin 3 half. So this is a quartet, 4-dimensional representation. So I should be going 3 steps. So let's see. So if I go here, first step, so E minus alpha 1, I will get, what I will get, 1, 0.
0 and
1, 1, 0, right? 1, 0. Then I apply again, minus alpha 1. So I will get here minus 1, 1. And then apply one more. Minus 3. 2, minus 3, 2, correct. Okay. You can see easily that this direction weight will be the same, because anyway, you see, as far as the weight is concerned, it's just additive. So whether you go this way or that way, whatever you will get, weight has to be the same. You're just adding the weights of these two to that. So which way, that doesn't matter. Okay, that, and similarly this one comes here. This is applying 2E minus alpha 1 and E minus alpha 2. Weights are the same if you go this way or if you go that way. I mean, to arrive here now, there are three possibilities, right? I can go like that, or I can go like that, or I can go like this. Okay. So there are several possibilities here. So here it was spin 1, so I should go one more step. So you get here 2 minus 2. Okay. 2 minus 2. 2 minus 2, yeah. But then again, this now becomes spin 1 representation. So I will go here with respect to the first SU2. So I will get here 0, minus 1, and one more step. Minus 2, 0, good, minus 2, 0. So that stops there, and once again, this apply. So this is E minus alpha 2, E minus alpha 2, E minus alpha 2. And here, you see this is a 3, so I should go, it's a spin 3/2, so it should be quartet, no? 4-dimensional. So I should be able to go one more step. So you get here minus 3, comma 1, comma minus 3. And this is a doublet from the first SU2. So I'm going to get here. So this is minus 1, minus 2. And this one. Yeah, this is the spin 1 representation from the second SU2. So this would have continued here. And it stops here, I think. That's it. Okay. So now you see, okay, we know the multiplicity of this is 1 because that's the highest weight. Huh? And this is a doublet of this, so this also multiplicity is 1. No? I come here, this is a spin 1 representation, so all of these guys must be multiplicity 1. Right? Here we don't know, because here there are two different ways of arriving here. Okay? You will find, if you just repeat that analysis that we did here, you will find that there are two states here. There are two linearly independent states. This way of coming and that way of coming is not give you independent states. But if this is 2, I mean, then you see, if you look at this SU2, there is a 4-dimensional representation, but that 4-dimensional representation will only include one of these states, right? So that means there is a doublet also. There is a 4-dimensional, and I mean there is a spin 3/2, and there is a spin 1/2 also. So there is a sum of two representations, spin 3/2 and spin 1/2. So, but whatever it is, the number 2 here should be also the same number 2, right? Because, yeah, these are plus 1/2 minus 1/2 spin, no? The numbers cannot be different there. They're the same. Even though from this point of view we see there are 3 possible ways of arriving here, but actually only 2 are linearly independent. This we could deduce without calculating once you know this answer. So this has to be done. This has to be checked whether these 2 are linearly independent or not. Once you know that, then this has to be the same number. And here it should be 1 because there's only 1 there. Okay. And then, now if you look at this SU2 chain, this is a spin 1. There's a 1 multiplicity here, so this better be also 1, So actually this, as far as this SU2 is concerned, there is a spin 1, that takes care of one state. Other state is a singlet. So, and similarly, if you now look, so this is 1, so therefore this better be also 1, because you know this is, I mean, if you look at this SU2, this is the spin plus 1, and this is spin minus 1. I mean the J3 quantum number minus 1. And here, where there are two states here, if you look at this SU2 chain, there is 1, 2, okay, this must be 1, but this must be 2, because this SU2 again, there is a spin 3 half plus a spin half representation. And so now if you, this is of course going to be the same, and now let's see how many states are there. So you have 1, 2, 3, 4, 5, 6, 7, 8, did I count correct? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9. 9 states in the boundary, right? Plus 2 times 3. Because these three states are each coming with a 2, multiplicity 2 times 3, that is 15. So this is a 15-dimensional representation. Okay. In general, there is a formula for this. If I give you these weights W1 and W2, so there is a formula here. I will just, without proving, I'm not, this proof is probably quite complicated. I mean, but the proof is, the formula is this: dimension is equal to W1 plus 1, W2 plus 1 times W1 plus W2 plus 2 divided by 2. That's the dimension. For SU2 it was simple, right? SU2 was 2j plus 1. But here it becomes a highly, I mean, like a cubic in the unknowns, no? I mean, it's so for example, so for this one it was 2, 1. So 2, 1, so this is 3 times 2 times 2 plus 1 plus 2, 5, divided by 2 is 15. That's the dimensionality. It's 2, 1. So this is again another example where you see there's a multiplicities are not 1. So this situation in SU3 is very different from SU2. In SU2, multiplicity was always 1, no, at every state. In a given representation, at every J3 quantum number was only 1 linearly independent state. Here it is not. Here it's, and it's happening because there are different ways of arriving. No? You arrive this way or that way. It's not a priori clear that it's going to be, I mean, the same state. No. Whereas in SU2 there was only one way of going. So it's, by construction, it was only one state. No. Here there are two ways of going. So that's the reason for this complication. Please check that. Check this thing. Whether again, just like that, what I did there for the joint operation. Just try with this to show that this there are two linearly independent states here. So in other words, E minus alpha 2, E minus alpha 1, acting on 2, 1, and E minus alpha 1, E minus alpha 2, acting on 2, 1. They are not, they are linearly independent. Okay, I think maybe I can just stop here now. And tomorrow we'll discuss the tensor product of SU3. And also then maybe I go back to SU2. SU2 also I didn't go too much on that. No? So maybe tomorrow let's do tensor products. And then from Wednesday onwards we'll start going to the general discussion.
Professor, could
yeah.
you suggest any reference textbook for today's discussion?
Frankly, I don't know. I mean, I don't know if there's any textbook which goes into these details. Okay, I have to search for it. I will search and let you know. Offhand, I don't know of any reference where they have done this. I mean, then in the standard textbooks, maybe they would do this for, say, fundamental representation, which means like 1, 0 or something to illustrate. But probably it will be hard to find any place where you would find for more complicated representations, like this 2, 1 and things like that, huh? In this language. But of course, there is this formula. This formula will tell you. I mean, even if you didn't know, by looking at this formula, you could have guessed that this should be 2. Because the periphery, in the periphery it will be all 1, 1, no? Multiplicity, because of these restrictions that these two must have the same eigenvalue, these two must have the same eigenvalue, no? Same multiplicity, and so on. So from that, the periphery of this diagram, it will be all multiplicity 1. The main issue is this one, these three. These three states are, but then we can see the periphery already gives me 9. I know the total dimension is 15 from that formula. So and we know that whatever this multiplicity is, it should be the same for all these three. So that immediately tells you it's 2 multiplicity. But from first principle, I mean, if you want to ask, this is by knowing the formula. This is more like a guessing game. But I mean, the actual concept of this thing, why this is 2 is this way of proving that there are 2 linearly independent states. But I don't know if there are any book. Maybe I will ask my colleagues and so on. Maybe I'll ask George if he knows some reference. Okay. Okay, so then we meet tomorrow. Okay, bye.